I've had my fiber laser for about a year and a half, and I never really had a need for a rotary, but I always kind of considered buying one, but was a little bit uncertain about how to connect it and if I could possibly do damage to the laser in the process of connecting it. But recently, a guy by the name of Peter Verdone bought a laser, and he immediately wired a rotary into his laser. And he was generous enough to share information about how to do it, including what components he used, and also the connector diagrams. So if you go to his website, and I'll put a link to it in the description to this video, you'll see exactly what he used and how he did it, and it's a pretty well documented process. So I'm going to kind of go through my experience with adding the same components that he added. So first, here are the components that I bought. This is the rotary chuck assembly, so it's got a 100mm chuck, which is actually kind of beefy. So the motor used on this is bipolar. It is a 3 amp motor, and it's 200 steps per revolution, so pretty standard. So here are the 4 wires coming off the motor. So this cost $245 delivered to me. Now the drive is from Stepper Online. You can also buy the same drive from a couple of different other places. I think Automation Direct also sells it. It's about $36 and it's pretty standard. So this is a DM542T. And this is going to work with pretty much any NEMA 17, 23, that kind of thing motor, any bipolar motor. Even if you're not going to use this chuck assembly, something similar, you're probably safe to use this drive. So in addition to the chuck assembly and the drive, I bought some cable, and this is just 18 gauge 4 conductor cable. You can kind of look in and see the 4 conductors, and it's also got a ground in there. I ended up wanting 5 conductors because I wanted to use the original connector on the back of the machine, which has 5 pins. And you may want to do that too, or you may want to cut it off and just start from inside the machine. Either way is fine. So I bought that. This cost about 20 bucks. And what I did with that cable was I stripped the jacket off, the insulation off, and I made this little connector out of it. So this plugs directly into the back of the machine. And this is a GX16-5 connector, and I bought a pack of, I think, 5 pair of female and male connectors on eBay for less than 10 bucks. So what you can do is just take 5 wires and solder them to the end of one of the female connectors, and I also put some heat shrink over it, and that's about it. Then it just plugs right in. So to do this, all you need is more or less a multimeter, because you probably want to trace the connections on the back of the machine, mainly the 5 pins. Make sure you know where they're going and they're actually going where you think they're going. I used a knife just to slip the jacket of this cable, wire stripper just to strip the ends of every cable I used, small screwdrivers to access, 1 to take these little plugs apart so I could solder them, and 2 to turn the screws on the stepper drive. And lastly, some hex wrenches just to open up the laser case. So let's take a brief look at the laser case. So most people have probably had theirs open if you have one, but what we have here is a 12 volt power supply, a 24 volt power supply, which powers the laser source, and a 5 volt power supply. So let's look at the back of the machine. So we have rotating shaft interface right here. That's what we're looking at, and you can recognize the little 5-pin connector. This is just the male side of it, and you notice there's a little nub right here that orients the connector. So I think this goes counterclockwise 1 to 5. So right there is pin 1, 2, 3 on the bottom, 4 right there, and 5 right there. So in order, I don't recall which one's which, but I think 5, or let's see, what is this? I think it's 1. I think 1 is the 24 volt positive, then 24 volt negative, then 3 is going to be your 5 volt positive, 4 is either going to be your pulse signal or your direction signal, and the other one is other. So pulse and direction are pins 4 and 5. Check Peter's diagram on that to make sure I just repeated it correctly. But what you can do is grab a multimeter, and you can come to the inside of that plug, which is right here. And this heat shrink isn't very good, so it's not actually glued on very well. So you can peel that back, and you can see the lead right there. It's soldered onto the connection. So you can put the lead of a multimeter on there, and you can trace that back to where it goes. So this one, the pink one, should go to 24 volt positive. And we know that our 24 volt power supply is right here. So if we look at our 24 volt section of this, positive section of this power supply, if you haven't looked at it before, you can kind of see these 3 terminals here are positive. These 3 are negative. That's ground, that's neutral, and that's the line. So this is incoming power. And if we flip it up, you can see positive is those 3. So if we look closely, you can see the pink wire right through the back there leading down to that terminal. So if you connect that with the pin that we think it is back here, then you can confirm that yes, that is 24 volt positive. And you can repeat that process for all 5 pins. So some of them are easy. The 24 volt positive and negative are just going to be found right there, and that black wire right there. So for pin 3, the 5 volt positive should be somewhere on this power supply. If you look at it again, you can see it's kind of a similar. You've got voltage positive and negative, and that's your ground. That's your 120 volts in. So it should tie right to that positive, this terminal right here. Now, on my laser, I found that that was not the case. And I initially connected everything, found out that the rotary didn't turn, and then stared blankly at the wall for an hour until I figured out, oh, there's my problem. This was actually tied. So pin 3 back here, that guy, it was actually tied up here to this. And I took this off and took this apart, and Peter's got a pin out for this thing so you can check it out. But it was tied to pin 11, which is a 5 volt negative. It's a ground reference pin. And that was doing nothing for me. So in the stepper drive, I need a 5 volt positive. Now in another diagram that someone else posted, they've got their rotary, the drive, going to pin number 5 on this connector. So I just moved pin 11 to pin 5. I desoldered and resoldered, and it works fine now. So I think that's all I needed to do. Pin 4 actually connects directly from this 5 volt power supply directly to the board here. And 4 and 5 are internally connected. This is pretty easy to do, to desolder, to unscrew this. It's not that bad once you get into it. So if your laser is like that as well, you may have to do that. This is just an eBay laser from from about 18 months ago. So if you bought one on eBay, you may face the same problem or you may not. So let's go back to the components. So let's quickly take a look at this stepper drive and see how it's actually wired. So let's look at the easy stuff first. So you can see these 4 wires down here lead directly from the motor, and they go to these 4 terminals at the bottom of the stepper drive. So you can see A positive, A negative, B positive, B negative. That means the motor has 2 coils inside of it, and the 2 wires coming from each coil are connected to each other. So if you pull out your multimeter and you just connect it directly to these 2 wires, you'll see continuity between a pair of wires and continuity between another pair of wires. And a lot of these motors are just plain labeled. They'll tell you which one is A positive and A negative and B positive and B negative. So that's not terribly difficult. And also you can see I flagged every one of these just so I could idiot proof it for myself. And I just did that with a little label maker. So beyond these 4 terminals, we have 2 more for your 24 volt positive that gives power to this entire drive. And then you have a ground here, which is going to be your 24 volt negative. So both of those are coming directly from the back of your laser if you wire it like I do and use this little connector. So you can see this is all leading from the same little group. So that's just giving power to your drive here. Let's skip over this middle section for the moment. That's just a bunch of dip switches on the side of the machine. It's really easy to figure out, but let's just skip it for the moment. These 2 we're going to completely ignore. These are enable and enable negative terminals, and what they do is they allow you to disable the whole drive when you put 5 volts to this terminal. And we don't want that. That's for other purposes. So the top 4 terminals are pulse and direction terminals. So what this is going to do, it's going to take 5 volts, and that's also coming from pin 3 on the back of the machine. And we're just going to jumper from that to the 3rd terminal, which is the 5 volt positive for the direction. So that's just establishing that we're sending a pulse from the JCZ board to this stepper so it gets to the motor. And the direction just says turn one way or the other. That is pin 3, as I said. And I believe, and again, don't quote me on this, but I believe these are pins 4 and 5, the stepper and pulse. So that's not terribly difficult to connect. The hardest part is probably if you want to connect it through this plug, just making the plug. That's probably the most time-consuming thing. So let's look at the little dip switches on the side of the machine now. You can see there are, 8? So that's when we come to these tables on the front. You can see this is a current setting. So how much current do we want to deliver to the motor? So we said this is a 3 amp motor, and you can see this RMS column right here and a peak column right here. So my understanding is motors most often are quoted at RMS. So when we say we have a 3 amp motor, we can probably stay well under that or right on it, more or less. I think Peter set his to 2.69. So that would be dip switches 1, 2, and 3 in positions on, off, and off. So let's look at dip switches 1, 2, and 3. So on is the down position, and you can see 1 is down, 2 is up, 3 is up. So we got on, off, off. So that's good. Then let's move down, and you can see we've got a little bit of text between the two tables that says switch 4, off equals half current, on equals full current. So that means in the motor's idle state, when you're not using it but it's powered on, how much current is being delivered to it. So if you were milling, using this on a mill where you want to establish a position, then hold that position very definitely, you probably want to use full current. In our case for the laser, we probably don't care, so off is probably fine, half current. So that will be in the off position, and you can see I've got it in the off position. So the last 4 switches are 5, 6, 7, and 8, and that's establishing how many pulses we have per revolution. So this motor is a 200 pulse per revolution motor. That's pretty standard. That means 1.8 degrees per pulse. You don't really need to know that. And I also have this reducer on it. You can ignore that. There is a little box in EzCad where you can put that you have a reducer, but either way, the pulses are going to be the same. So you're choosing how many pulses. My understanding of pulses is that the larger the number is, the little bit more current you'll need. So I've seen most people say that their Chinese lasers, Chinese rotaries, as they're delivered, come at 6,400 or 12,800 pulses. So I've set mine to 12,800. That means the switch 5, 6, 7, and 8 are going to be on, off, off, on. So if we look at the switches once more, we've got 5 is on, 6 is off, 7 is off, and 8 is on. So that sounds right. So that should give us 12,800 pulses. And you just enter that number directly into EzCad on the screen, and I can show you where that is. So really the only hiccup I ran into was when I was trying to find my 5-volt positive and it linked up to a 5-volt negative. So other than that, it was a relatively smooth process, and I have tested it and it does seem to work. Okay, so I've connected the rotary, and I chose to put the stepper drive along with a separate 24-volt power supply into a little polycarbonate box in the back and power it separately for the moment. Eventually I'll probably move the stepper drive probably right up here or somewhere inside the case and not run a separate 24-volt power supply. I'll just run directly to here, but for the moment I've isolated the 2 leads coming off of the GX16 connector on the back. The only reason I'm doing this is so I don't have to have the actual laser source powered up. Okay, so I'm going to leave the camera pointed at the top of the chuck here, and keep in mind that's a 100mm chuck. So we're going to jump into EzCad and look at the settings that we need to set up this thing for the first time. Okay, so we're in EzCad. All we need to do is jump up to this laser menu at the top of the screen. We'll go to Split Mark 2. And you can see that we have a couple boxes here, but for the moment let's just focus on the center where it says axis step, and it has an up and down arrow. What we can do is put in a dimension in millimeters that we want the rotary to turn. In order to make sure that we're turning the right amount, we need to make sure that our stepper drive pulses per round agree with what it says in EzCad. To do that, we go to the parameter menu right here. And if you notice, the first box we have available here. So on steps per rotation, if we had 0 half-stepping, micro-stepping, anything on the driver, we would leave it at 200 because this motor has 200 steps per revolution. But since we're using the driver and we have it set to, if you recall our dip switch setting, it's 12,800 steps per rotation, that's what we need to put in this box. So 12,800. Now, I said for my case, and probably for nobody else's, I have this 6-to-1 reducer, so I need to account for that gear ratio as well. So if you look over on the right side of the screen, we have a little box that says rotate axis and gear ratio. So we need to put a 6 there. And notice we also have a part diameter. Now, I've got the light shining right on the top of the chuck, and remember this chuck is 100mm. So I'm just going to put in 100mm. So I'm going to say OK. And if we change our axis step to go all the way around the chuck, that'll be pi times 100mm, which is 314.15. And that should return right back to the little dot I drew on here. So let me make it bigger. You can see where we are. We should get right back to that same point when I press the up arrow. And you can change the speed this rotates as well. Well, that looks pretty close. That looks okay to me. So that's basically what I've done for setup, and you may notice that I have a little 8mm pin sticking out of the chuck. So I'm going to set this off of there, kind of center it. I'm already focused to the correct height. So let's quit this screen and quickly jump into Rotary Mark. So I've just got a sample piece of text on the screen oriented vertically, and it is hatched at 0 degrees, and the line spacing is 0.05 millimeters, and you'll notice our split size is also 0.05 millimeters. So the total height of this is set to 25 millimeters, which is approximately pi times the 8mm diameter. So it should wrap almost all the way around the pin, just short maybe 0.1 millimeters, and the height is going to be about 8 millimeters. Alright, so there's our result. Let's take it out of the chuck. So you can see the starting point pretty much matches the ending point, so that's pretty good. If anybody has any questions, comments, feel free to chime in the comments below. Thanks for watching.